Let's talk about Cheng Xinru. I'm going to talk about this. She was born in 1912. She was also known as the first lady of physics. Now, she was an American, but she was also, of course, American Chinese nuclear physicist. Most commonly known for her work on the Manhattan Project. If you don't know what the Manhattan Project was, that was the project where they were building the nuclear bomb that they would then use on Hiroshima and Nagasaki. The process involves separating uranium-235 from 238, which is not an easy thing to do. It's hard to it's hard to it's hard to separate elements as it is. It's even harder to separate elements when they're exactly the same. It's hard to separate isotopes because ultimately the only difference between uranium-235 and 238 is 3 lousy little neutrons. So it's very difficult. She was also conducting experiments establishing whether or not the conservation of parity also applied to the weak interaction. Now, I'm not going to talk about what that means because it's a bit complicated. She lived and worked through both World War I and World War II and the Great Depression. She married Luke Yuan, I'm not going to even try, in 1942 at age 20, and later had a child with him named Vincent. Theoretical physicists Dao Li and Chen Liangming, who originated the idea of parity non-conservation and proposed the experiment, received the Nobel Prize in 1957. Chen Shung, her contributions were honored in the acceptance speech, but her participation was not recognized until 1978 when she was awarded the first Wolf Prize. So she essentially came up with a lot of these theories, but they just sort of ignored her. It was kind of it was interesting here because it looks like the blame isn't to be put on these two scientists, but because they acknowledged her. But my guess is it probably falls to the Nobel Laureate Society for not choosing to award her in the Nobel Prize. So I don't know how you want to think about that. I still think it's a stolen idea in that way, that her experimental ideas were stolen. But yeah, it's also another woman in physics and maths that has had their ideas stolen and stuff like that. I'm not sure if you guys have seen it, but there's actually a bit of a viral video that came out a couple of days ago about a woman in I didn't actually see the video, but I saw the news article about a woman who in STEM who was being completely ignored, and by her male classmates. And it's like, well, I've seen this happen all the time. It made me think of this whole thing, and yeah, it's really hard for me. I know that I've got a couple of very, very intelligent women in this class, and it makes me feel really bad that I know that some of the women that I teach in engineering will probably give up engineering because it's such a male-dominated field, and that always annoys me. I know that there's a lot of gentlemen here, guys. I always want you to remember that, just because you're a man does not, and this includes myself included here, just because I'm a man doesn't mean that there aren't engineers that are women that are way better than me. And there are definitely many physicists that are way smarter than I am that are women. So just, try to, be a bit more humble. Anyway, sorry, off topic, completely random. Let's get back to the point. Sorry about that, guys. Lesson 21, conventional current. We will explain how moving charge creates a current. Today's job is to try and talk about this first idea of electricity. Electricity can be thought of in 3 main ideas. It can be thought of as voltage, current, and resistance. There are 3 main ways to talk about how electricity exists. So the first one we're going to talk about is the hardest one, is current. We're going to talk about how what current is and how it works. Leading up to this, what did we do at the very end of last term is we talked about the history of electricity. First, we talked about how rubbing amber actually caused an electric charge, which caused objects to move. We talked about how that charge could be stored in a Leyden jar, and then later on how that charge could be made using a voltage pile or a battery. Electricity is the process in which charged particles, in this case electrons, are moved from one location to another. And what I did is I actually spent some time talking about why electrons move. The main theory for why electrons move is to balance charge. And then I talked about, well, how can you cause an imbalance of charge? Why do they want to balance the charge for? And yeah, that's essentially why electrons move. And so then I talked about, well, we can take advantage of that. We then spent our lesson, this was the Thursday lesson, talking about scientific notation. What we did in the scientific notation lessons, we talked about how you can turn 52,000 into scientific notation, which in this case would be 5.2 times 10 to the power of 4, because I have to move this 1, 2, 3, 4 to get to it. Whereas something like this is going to be 2.5 times 10 to the negative 5. Because I have to move this decimal point 1, 2, 3, 4, 5. Or you can count the zeros in front of that 2, either or. And because I have to make this number from a small number into 2.5, I put a negative out the front. Then we talked briefly about these kinds of facts. I actually extended some of this information to after the lesson, but I did talk about rates. I talked about how you can convert a rate to something else. A rate, by the way, for those of you that don't know, is how 2 units change. And that's what we did at the very end of last term. We're going to start by talking about conventional current. Now, the first place to talk about conventional current is to start off with this idea of electrons. Okay? Now, if I've got an electron sitting just, I've got a group of electrons, I need a way to refer to these electrons. How much charge does an electron have? How fast does an electron move? How much does an electron weigh? How many electrons? And so we need to actually understand the electron before we need to understand the electron before we can even start to understand anything to do with electricity. So to understand the electron, we're going to start off with Charles Coulomb. He's the person I usually go to when it comes to describing electricity, and this is normally where I start, is electric charge. We said that electrons move because they want to balance out charge, so we should start off with understanding of, well, how do we measure charge? So how we measure charge is because of Charles Coulomb. And Charles Coulomb suggested this. He said, charge is measured in coulombs, named after himself, and it has the symbol Q. So the symbol for charge is Q. Okay, that's measured in coulombs. And so that's fine, great, cool, whatever. That's not very useful until we introduce this fact. 1.6 times 10 to the negative 19 coulombs is the charge on one electron or proton. So if I have one electron, it has a charge of 1.6 times 10 to the negative 19 coulombs, or C. That's a very, 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 very small number. That's a very minuscule number. Essentially what we're saying is that an electron barely has any charge at all. Okay, and this is why, by the way, ladies and gents, I introduced you to scientific notation so early. That negative 19 means that if I was to write down this charge properly, I'd have to have 1/6, and then I'd have to have 19 zeros in front of it. So that's a very, very, very small amount number for the amount of charge. So that means if you want to get a decent charge on something, like if you want to get a coulomb of charge, you're going to need a shit ton of electrons. Yes, I did just swear there, I don't care. You're going to need a lot of electrons to do it. So let's quickly do this one. How many coulombs of charge would I have if I had 2 electrons? If the charge on 1 electron is 1.6 times 10 negative 19 coulombs, how much charge would 2 electrons have? Can I get a guess in the chat? Can I get someone brave enough to, even if you want to do it privately, tell me how much charge do you think that 2 electrons would have? Just a guess in the chat or out loud if you want to unmute yourself, that's fine. Waiting for an answer in chat, by the way. If you're tuning in and being like, why is he so quiet? It's because I want to know how much charge is 2 electrons going to have. Got an answer, and it was 3.2 times 10 to the power negative 19. That is correct. If 1 electron is 1.6, if this is 1 electron, if I had 2 electrons, I just multiply 2 times 1.6 times 10 to the negative 19. 2 times 1.6 equals 3.2 times 10 to the power of negative 19 coulombs of charge. So barely anything. Again, so you need to have like millions upon billions upon billions upon trillions of electrons before you start to see like a noticeable charge. How many coulombs of charge would I have if I had 6.2 times 10 to the 23? I'm going to do this one. So when we have 2, we just multiply 2 times 1.6. When we have 6.2, that's a large amount of electrons. 6.2 times 10 to the power of 23 times 1.6 times 10 to the power of negative 19 equals. Now, because I know this is a positive and this is a negative, and this is 23, which is larger than negative 19, I know that the power at the end is going to be about 4. But I could do this on my calculator just to be sure. 6.2 times 10 to the power of 23 times 1.6 times 10 to the power of negative 19. And you're more than welcome to do this in your calculator. Equals 99,200 coulombs, or 9.9 times 10 to the power of 4 coulombs. There's the 4. So that's just a different way you can do it. Now, there's one more thing, and this is one of the reasons why I get you guys to spend so much time working on rates. Because I'm going to ask this question here. How many electrons are present in 1 coulomb? 1 coulomb. If I have 1 coulomb of charge, how many electrons are there? Now, does anyone know what I would need to do in order to figure this out? How would I figure out how many electrons are present in 1 coulomb? Who wants to take a guess on what I would need to do? Don't you move everything to the right? Sort of. Good guess from Oliver there. What you need to do is this. You need to think about it. I've got 1 coulomb from charge. I want to know how many electrons you need to make up 1 coulomb. So if I know the charge on 1 electron is this many coulombs, right? It's a very, very small number. I want to know how many of these fit into that. So that sort of should tell you you need to divide it 1 coulomb divided by 1.6 times 10 to the power of -19 electrons per coulomb equals. I think the answer should be 6.25 times 10 to the power of 20, but let me just double check. That's just based off memory. 1 divided by 1.6 times 10 to the power of -19. 6.25 times 10 to the power of 18. 6.25 times 10 to the power of 18 electrons. That's like about billion, trillion, quadrillion. That's about like 6.25 septillion electrons. That's a huge amount of electrons. You do divide them, so someone did figure that out. Really good. So that's a huge amount of electrons, and that's why it's important to understand how these rates work. If I tell you that I've got 1 electron is 1.6 times 10 to the -19 coulombs, and I give you 1 coulomb, you need to divide it. If I give you 10 coulombs, you need to divide it. You guys can work that out. But this hopefully gives you a bit of an idea of how many electrons go into 1 coulomb. That's such a huge number. Even if you were just to look at like a millicoulomb or 1,000th of a coulomb, it's still going to be like times 10 to the power 15. So essentially electric charge, but is, yeah, pretty large. So, yeah, so electric charge is where we start. But, okay, but that's fine. That gives us a good way to talk about static electricity. If you build up a charge on a Van de Graaff generator, how much charge is there? But any electricity is very rarely is static. Normally when we look at electricity, we talk about movement. We talk about how quickly does the electron move from one place to another. So, and that's essentially what electricity is. So in order to get a good idea of that, we need to move away from electric charge and move into something called current. Now, the scientist we have to thank for our understanding of current is André Ampère. He was a French scientist, and he came up with this idea called current. And his idea for current was this. Current is the flow of electric charge. It has the symbol I. Now, hopefully you guys have been like, what the hell? Charge has the symbol Q, even though there is no Q in charge. Because current has the symbol I, which is again very odd, but still that's what they use. I think the I comes from the word imperatus, which means to move, but it's not for certain. I don't really remember exactly. I'm not a Latin speaker. Impello, something like that. It is measured in amperes. Obviously, again, André Ampère names current after him. So we're talking about the movement of charge. Okay, so how quickly does charge move? How quickly does electrons move? 1 amp, 1 amp is 1 coulomb per second. So if you have this 6.25 10 to the power of 18 electrons moving in 1 second, you've got an amp. And there's a nice formula that we can use for this. I equals Q over T, where Q is given is that charge equal, T is our time in seconds. So that means that if I know these facts, I can sort of backtrack. Let's actually do an example. If I had 22 coulombs of charge pass through a wire in 8 seconds, what is the current? This is a pretty easy one. I'd like you guys to work it out for me and put it in chat. What is this current? What current is going to be made by 22 coulombs of charge passed in 8 seconds? Have I got any guesses yet? No, not yet. Still waiting. What is the charge in amps? If 22 coulombs are charged past 8 seconds. 2.75. Do I think 2.75? That sounds pretty close. Probably is it. It is 2.75. Great. Remember, current is equal to charge over time. If I've got 22 coulombs divided by 8 seconds, means that I'm going to have 2.75 amps or 2.75 coulombs every second. So that's what amps are, how amps are measured. You could even take that, how many electrons pass through in 1 second. If you know that 2.75 amps means you've got 2.75 coulombs every second. And we know, how do we work out how many electrons? Well, 2.75. How many of these electrons can fit into that 2.75? That means every second, pardon me, it's been a long day for me, guys. There's 1.72 times 10 to the power of 19 electrons. But that's a bit of an extension. So that gives us current. So charge is measured in coulombs, and current is measured in amps. Current is how quickly how much charge is moving and how quickly it is moving. If you had a lot more charges moving, then you could get a higher current. So that's what we have when we look at current and what current sort of means. So let's now look a little bit more in depth into this idea of moving charge. What does current mean? There's no pencil on this one, so you don't have to copy anything down like you did for these two. Now, if you didn't copy anything down because you forgot, luckily I'll be putting this up on YouTube at some point this afternoon. So current can be thought of, there's lots of analogies we can give in current, but it's the movement of charge. So if I was to have this big tank of water, which is like a battery, this pipe, which is like a wire, and a tap, which is like a switch. And I was able to say to you guys, what if I asked the question, when the tap is switched off, is there any flow? Can I get a quick answer? This is an easy question here, so if you don't know, easy question. Is there any flow when the tap is switched off? What do you guys think? The answer, no. There is no flow. There is no movement of water. There is no movement of charge. There is nothing. That's exactly true, the same as a circuit. If you wire up a circuit and the switch is closed, there will be no movement of charge. But when you do switch the tap open, there will be a movement of charge, and that is a current. Current is the movement of charge from one place to another place. Now, so how does this look for an actual circuit? Well, if I take a battery and attach it to a light bulb, you guys should be able to remember from the other, or you probably won't remember, so I'll quickly go through it. The negative side means we've got a surplus. We've got lots and lots and lots and lots and lots of electrons. And in the positive line, we've got very, very few electrons. So these guys want to balance out the charge. The best way the electrons can balance out the charge is by going through this wire and getting to the top. You can't really go through the battery because that won't work. But you can't do that if the switch is off. If the switch is off, these electrons can't move. There's no electron movement. There is no current. When the switch is off, there is no current. If I switch that switch on, though, then the electrons can go through it to get to the positive side, and that's how we can create a charge. That's how we can create a circuit. That's how we can create a current. So current needs to have a completed circuit in order to work. Most of you guys probably know that from year 9. You can't have any gaps in the circuit or else it won't work. Now, here's a question. Would this work? Would this turn the light bulb on? Got one guess. If I got another guess, can I get another guess? Would this light bulb be switched on? And if you're brave enough, could you say why won't this light bulb be switched on? Or if it is switched on, why is it switched on? Up to you guys for your guess. We have one guess so far. Okay, I'm going to answer this because otherwise we'll be here all afternoon. No, this light bulb won't switch on. Because if you imagine, just like the other time, although there is one wire, there is no wire here. There is a gap between the negative and the positive and the battery. So therefore, that won't switch on. What about this one? Any guesses? This one won't switch on either. No, because again, even though there is, this wire goes to the positive and this bottom goes to the positive. Nothing is attached to the negative. This is missing. There is no wire here. So therefore, it won't conduct. This light bulb will switch off. But if I switch it like this, then yes, this will conduct. The reason this does conduct is because the negative can go up to the battery and through into the positive. Even if there is just one wire, you don't need to have more than one wire. With just one wire, you can get this light bulb to switch on. And what do I want you to copy down, at least for the basics for this, is this idea here. Charge must always move in a cycle that allows negative charge to move to positive charge. If there is no way for a cycle to exist or for the electrons to move, there will be no current. I'll give you guys a fraction of a second to jot that down. And then we're going to move on. Okay. So let's now talk about, so this is a closed circuit, that's great. What else can we talk about with regards to current? Yeah, this is just another picture, the closed circuit. So the current can move around in a circle. The next is to talk about, well, okay, so electricity is the movement of charge. Great, cool, I understand that. But there's actually this extra little idea here that I always like to draw attention to. Often people think, when I start to say electricity is the movement of charge, people start to think of wires like this as like big long tunnels. And the electrons go in one side and come out the other. And they get this idea that, you know, they get this idea that when we talk about current, we talk about how many electrons are moving down this tunnel. But the problem with that theory is this. Electrons, if you think about a modern wire, it's not a hollow tube. A modern wire has a bunch of stuff in the middle. It's got a bunch of copper and plastic and air. So that's not actually how electrons move. They don't move through this pipe, through a wire like a pipe. Electrons actually do it a bit differently. I'm going to show you how. This picture, this is a GIF, but it's probably one of the best GIFs I've found because it explains this so well. Electrons don't move very far down a wire. You might think that they fly down like a tube, but they don't. They don't move very far at all. What does move, the current, is simply how quickly the charge is passed down a wire, not how quickly the electrons move. We're talking about the charge. The best way to look at this is this picture below. I want you to watch this new electron. And it jumps. And it jumps again. And it jumps again. And it jumps again. And one more time for good measure. So that took a very long time for the electron to move. These electrons are slow. But now I want you guys to focus on this red dot. This red dot represents the movement of charge. I want you to look at how quickly the red dot goes from the left to the right. It's very quick. So the idea is, even though the electrons don't move very much, and that sort of makes sense, hopefully you guys understand, if the electrons moved, all of them moved out of the wire would have no electrons, and so it would start to fall apart. So the electrons don't move very fast, but the charge does. If you think about the charge as these negative electrons moving to the left, or as a positive charge moving to the right, the speed that these things move along is fast, and that's what gives it the current. And that's why we spend so much time saying electricity is about charge rather than just this actual atom. I'll give you guys a second to copy this down, if you haven't copied it down already. Next up, so yeah, and this is actually probably one of the difficult ideas, and it's one of the ideas that I think is actually pretty important to teach, because a lot of people think, oh man, that electrons just go down like a wire, like it's a tube. It's like, well, no, they don't. Actually, barely any electrons move at all. It's actually just the charge that gets moved. So I want to talk about this now, which is just a bit of a description of current. Now, when we have a wire, we can draw a wire in two ways. We can draw current in two ways. We can draw current coming out of the positive and going into the negative, or out of the negative and into the positive. Now, you might think that one of these ways is correct, but actually both of them are sort of correct. Conventional current assumes the current flows out of the positive side of the battery, through the circuit, and back to the negative side of the battery. This was the convention established when electricity was first discovered, but it is incorrect, because that's not the way the electrons move. They originally thought the electrons were positively charged particles, but they later found out they were negatively charged. You might think, how did they get that so wrong? Well, look at this picture here. In this picture, we've got a positive charge quickly moving to the right, and a negative charge electrons moving to the left. So you could instead think of, if you just swap the charges and made electrons positive, then it would work just as fine. So that's what they originally thought with conventional current. They originally thought conventional current was this movement from the positive to the negative. We later figured out the electrons are negative, and that's not the way that it works. Because the electrons are negative, we actually figured out that it's what actually happens is the electrons are the ones that are moving. The electrons come out of the negative side of the battery, because when you have a buildup of electrons, like in the negative side of the battery, that's what makes it negative. They move through the circuit to get to the positive side. And that's what we refer to as electron flow. So because that's the flow of electrons. The electron flow looks like this. It comes out of the negative and goes into the positive. Whereas the other one, conventional current, is the opposite. It comes out of the positive and into the negative. It comes out of the positive and into the negative, even though that's not the way that it actually works. Now you might be sitting there thinking, oh my God, why is Sir teaching us about conventional current if it's wrong? Surely that doesn't make sense to teach us something that's wrong. And yeah, sure, that's not the way the current works. But this is one of the rare times that science has hung on to something weird, because engineering versus science, the direction that the current flow does not affect what the current is doing. Thus, it doesn't really make any difference which convention is used, as long as you are consistent. So it actually doesn't matter whether or not you are going from the negative to the positive or from the positive to the negative. It doesn't really make much of a difference. Because ultimately, what is the difference between positive or negative? Like if I gave you the classic example I usually say is, if I gave you a rod and said this rod is negatively charged, and then I gave you another rod and said this rod is positively charged, how would you tell the difference? There is actually no real way for you to properly tell the difference. So therefore, it doesn't matter. Both conventional current and electron flow are used in general. In general, the science disciplines use electron flow. So if you're studying chemistry or physics, you will more often use electron flow to describe electron movements. But in engineering, we actually use conventional current. Actually, to be honest with you, in physics, we use a lot of conventional current as well. I've only ever really used electron flow properly when I've been doing it in chemistry, and you're talking about actual electrons moving. But for all circuit diagrams that we'll be using, that get used every day, all the diagrams that you might find for electronics in your calculators, in your phones, they all use conventional current. Now, because this is an engineering class, we're going to be using conventional current, which means it comes out of the positive and into the negative. If you do get a little bit wrong though, don't stress yourself too much, because remember, it doesn't matter too much. But there will be some times where it does matter. And they're going to be, when we get to those times, I'm really going to make sure that you guys understand it. So let's summarize this into one quick page. I'd like you to copy this down, please. And if you notice, I've squashed all the text down into a small idea. Conventional current is the direction of current from the positive end to the negative end. Electron flow is from the negative to the positive. And we're going to be using this one. It's kind of weird. I've already taught this same lesson remotely already. So actually, if you want to go back, you can actually see me re-explain this in a slightly different way if you already want to look on YouTube. So it's going to be a bit weird because I'm going to be repeating the same lesson, but that's fine. Now, Okay, what's next? So let's see. So far we've covered charge. We've covered current. Current is the movement of charge. Charge is measured in coulombs. Current is measured in amperes. We said in order for a current to move, though, we need to have a completed circuit. If it's not complete, there's no movement. Completed circuit means you have to have a negative and a positive connected. We've then talked about, well, which way does charge move? Does current move? Current moves from the positive to the negative according to conventional current. And that's the one that we're going to be using. Even though in reality, it's not the positives that are moving, but it's the negatives that are moving, which is why we also have this idea of electron flow. It's one of those weird quirks of history. I reckon if someone had suggested that the things that are moving are the negatively charged, we wouldn't have this problem at all. But alas, that's just the way things happen. Now, what time have I got? Okay. It's 2:28. I'm going to explain briefly. Let me see. Okay, I'm actually going to show you guys. I'm just trying to. Okay. What I'm going to plan to do now is I'm going to go briefly talk about this top idea here, and then I'm going to finish up by going through voltage, even though it's sort of technically in the next lesson. Because this is a double lesson, I really want to take advantage of it. So I'm actually going to look at one of these, this top question here. So this was just getting you guys a chance to sort of practice some of these ideas. Let's talk about this here. A circuit is running a light bulb at 40 milliamps. If 1.5 coulombs of charge has passed through the globe, how long is the circuit been on for? So let's look at this. The current is running a light bulb of 40 milliamps. 40 milliamps means that we've got a current, which is the symbol for current is I, equals 0.04. If you want to amps. Milli means 1,000th. So that means you've got 40 times 1,000th, or 40 times 10 to the power of -3. Doesn't matter, as long as you understand that 40 milliamps is actually something like this. It's kind of like saying 40 meters, 40 millimeters in meters is what. And then we've been given this charge, which is Q of 1.5. And it asks us for how long the circuit's been on for, which is T. How long this circuit has been on for is actually going to be, if I equals Q over T, then that means T equals Q over I. If I have 1.5 divided by 0.04, that's going to give me the amount of time it's going to be on for. 1.5 divided by 0.04 is 37.5 seconds. Now I'm not going to go through this question here because I've already done a very, very similar question to this. But again, we know now that 1.5 coulombs of charge have passed through, and we know the charge on one electron is 1.7 times 10 to the -19 coulombs. You can see how many of these coulombs can fit into that 1.5 coulombs. Now, I'm going to finish this lesson off. I've got about 35 minutes actually, but I'm going to finish this lesson off by quickly talking about voltage. Now, voltage is going to be the last topic that I'll talk about today, and it's going to be the next big topic. So all of the lessons so far, the first hour of the lesson has just been about current. The next 15 to 20 minutes, though, is going to be about voltage. So voltage is linked to the amount of energy the electrons have. It is measured in volts and has the symbol V. Discovered by Alexander Volta. He was the one that popularized it. Now, there's not much to copy down on this slide, so I'm going to actually spend more time trying to get you guys to understand what this idea of voltage means. So, voltage. Current is about how much the electrons are moving. It's how quickly they're moving, which way they are moving. When we talk about current, we talk about movement. But when we talk about voltage, we talk about how much energy those electrons have. How much of a punch do those electrons have? How readily do they move from one place to another? That's what we talk about when we discuss voltage. So the picture at the bottom here I've got two electrodes. And in these two electrodes, there is electricity moving from one side to the other. Who wants to take a guess, by the way? Which side are the electrons coming out of? Are they coming out of the left side, or do you think they're coming out of the right side? It's a 50-50 guess, ladies and gents, so I want everyone to give it a try. Which side do you guys think that they're coming out of? Are they coming out of the right, or are they coming out of the left? 50-50 guys, there is absolutely no shame, and you can guess and still get it right. Correct. What do you guys think? We've got 3 guesses. I want to see, let's go with 6. I want to see 6 guesses. I've got 4 guesses. Who else wants to guess? Most of the people are guessing privately, and I'm not going to pick on them. And all 4 of the guesses that have come in so far have been the same answer. So I'm pretty confidently saying which one. I want to see 2 more guesses. Which side are the electrons coming out on? The left or the right? Okay, someone's got an interesting different answer. I like that. Someone said both. And I'm like, okay, good. Let's see what else have we got. One more answer. I'm looking for number 6. Who's going to give me lucky number 6? Which side are the electrons coming out of? The left or the right? Come on, who hasn't given me an answer? I mean, like Thomas, you haven't given me an answer. Looking at Ricardo hasn't given me an answer. Some people that could just guess left or right. Eric, haven't got an answer from you. Everest, you can give me a guess. Which one? Give me 50-50. Ryan, who wants to give me a guess? Which side are the electrons coming out of? The left or the right? Who wants to take a guess? One more guess. Thank you, Dylan. Dylan guesses the right. Out of the 6 guesses, 5 people said the right, and it is correct. The electricity is coming out of the right. The reason I can tell is because the electricity is coming out of one point here, but going to several points here. Now, it'd be very, very difficult. Yeah, it's because it disperses from the right. Good job, Dylan. It's because it'd be very, very difficult for all of these electrons to say, coordinate and say, let's all line up and attack the same point. It's a lot easier to explain electrons all coming out of this side and then making their own way to the right. So This is a current. It's a movement of charge from one place to another. But what has this got to do with voltage? Well, the reason I say voltage is this, okay? If you imagine, your wall socket, the place where you plug your laptop or your phone in to charge it up, you don't see electricity fly out of there. You don't see electricity jump from there to the ground. And that's because the voltage in your wall socket is not large enough to jump out of the wall. It needs to have, your electrons need to have a lot of energy. They need to be really pumped up with energy to jump through air. Because it's very, very difficult to jump through air, you need to be carrying a massive punch in order to get through. You might think of, okay, when you, for example, let's take another example. Let's talk about the voltage from the wall. Now, the voltage from the wall is very, very powerful. So if you compare the voltage, how quickly your phone charges from the voltage from the wall compared to how quickly your phone charges from a power pack, it's going to charge faster from the wall because the wall has got a higher amount of energy. It's got more push. You could also even think about something like, I don't know, a fridge. You couldn't power maybe not a fridge, maybe like a washing machine. You couldn't power a washing machine with a battery because it needs so much voltage. It needs so much energy to get a washing machine to work. That's why you need to plug it into a wall. So when we talk about voltage, we're talking about how much of a punch those electrons have. And their punch, the amount of punch that each electron has, is measured in volts. So we're going to extend this idea to talk about, well, we'll talk about energy briefly. Now, I like to think of voltage in the same way that I think of energy. Now, this is a bit of a weird example, but I like to sort of bring this up because I've had some students in the past that have not really understood this concept. So I'm going to show you guys here. On the left, I've got, what I'm going to do is I'm going to lift this apple up, say 8 centimeters off the ground. And then what I'm going to do is I'm going to lift these electrons 8 centimeters away from the positive charge. By moving the apple against the force of gravity gives it potential energy. Now, potential energy is a pretty high level concept. You may not be familiar with potential energy because it's more of a VCE concept. So I'm only going to briefly talk about it. But obviously, the idea is that gravity wants to pull this apple down towards the earth. And so by pulling that apple upwards, what you're doing is you're saying, screw you, Earth, I'm going to pull you against, I'm going to do something against you. I know that you want to pull that apple back towards the earth, but you know what? Stuff it. I'm going to pull it up. And that gives that apple some energy. If you let that apple go, it'll fall towards the ground and release that energy. And that energy will be turned into movement and then into, like, you know, squashing the apple. But if you pull it up, you've given it energy. When you pull the electrons up, it might not be apparent, but you're doing the same thing. These electrons want to move down back towards the positive because negative is attracted to positive. But by moving them up, by moving them away from the positive, you're giving them energy. By moving electrons away from the protons against the electrostatic force, see how gravity, electrostatic, gives them potential energy. just like this. We call that potential energy voltage. When you lift up an apple, we don't have a name for that potential energy. We just call it gravitational potential energy. But when we lift up electrons away from protons, we give that a name. We call that energy voltage. So it's just a quick thing. This is a bit advanced. This is a bit of a year 11 physics concept. And if you don't grasp this straight away, that's okay. But I just want you to understand that that's what we're talking about. So that means you can actually build up a large amount of voltage in a battery by just separating more and more protons away from more and more electrons. The more you separate them, the more electrons something has, and the more the electrons want to get away from where they are, the more energy they have, the more voltage they have. So Van de Graaff generators have a huge amount of voltage. Batteries, a 9-volt battery has 9 volts of energy. That's how much extra energy those electrons have. They will push through a circuit to complete them. So what is a voltage? Voltage can be thought of as, like, again, the energy or the pressure. In this case, the tank or the battery is full of energy. That water in there is pushing to get out of that tank. It wants to get out. Now here's the question. When the tap is switched off, is there any pressure? I'm actually going to ask this really quickly to chat. Is there any pressure when the tap is switched off? Yes or no? (50-50) guys, yes or no? Dylan, you might want to answer this because you're doing a bit of a role. I'm actually looking at you. Maybe Elaine might want to give it a guess too. Is there any pressure when the sorry, I didn't hear the question. Well, let me say it again. Is there any pressure when the tap is closed? I got 1 guess for yes, 2 for yes, 3 for yes. Yes, there is. Now, unlike, and you're correct, unlike in, thanks, I got 1 answer from someone who hasn't given an answer before. Really good. Yes, when the tap is closed, you cannot get, there is still pressure. There might not be any current, but that water really wants to get out of that battery. Just like if you took a battery just sitting on a table, the electrons don't want to be split apart from the protons in the battery. They want to complete the circuit, but they just might not have enough energy to jump. So if you have a battery, right, let's just say one of the classic, if you have a battery, let's just say you got one of those square ones, the electrons don't, and you got this negative side here and a positive side here, the electrons here don't want to be here. They want to be over here, but they don't have enough energy to just jump through the air. That's why they need a wire. So there's still pressure, there is still voltage. And then once I open the tap, there is still pressure. In this case, once I complete the circuit, the pressure doesn't go away. If anything, the pressure is exactly the same. Because now all that pressure is going to push electrons through the wire until it gets to the other side. And so we can, even wrapping it up again, here's a picture. Is there, the battery provides the voltage that will push the current through the electrons. If you think about it, the electrons here, they don't want to be in the negative part. They want to be in this positive part. So because of that, they will push their way, or they will push electrons into that. And that push is what creates the current. If there's a big push, there will be a high amount of current. If there's only a small push, there will be only a small amount of current. And that, the next part is resistance. And I think that resistance is going to be for Wednesday's class. So, ladies and gents, that's all I'm going to teach you guys for this topic today. So what we've done is we've covered four main ideas here. We've discussed charge, which is measured in coulombs. We discussed current, which is measured in amperes. We discussed completing the circuit and also the different types of circuits, like the different ways in which the current can move around a completed circuit. And then we talked what voltage is. Voltage is the energy or the push the electrons have. More push means that they can move more current. They can start jumping through water, through air, through other things. And yeah,